Today, we want to look at families of functions and talk about modifying graphs, the effect that these modifications to the function have on the graph of the function. And we looked at two cases. We looked at two operations that we could apply before or after a function. We've got addition and multiplication. Two good ones to start with. Now, the addition or multiplication can be either applied before or after the function. So if we look at this function, this y equals d plus a times f of b times x minus c, we have each of the four modifications where f of x is a function, a, b, c, and d are constants. If we think about the order of operations, like plugging something in for x, the first thing that happens is we subtract c. That's first operation. The second operation that happens after we subtract c, we multiply by b. So number two operation is multiply by b. The third thing to happen is take the results and plug it into the function. So the function is step 3. So b and c are modifications that happened before the function. Once we get the result of the function, we multiply by a, and then finally we add d. So the multiplying by a and adding d are operations that happen after the function was applied. So there are 5 things happening here. First, subtract c. Second, multiply by b. Third, apply the function. Fourth, multiply by a. Fifth, add d. Now, each of these modifications is addition or multiplication. And we saw last week with the function e to the minus x squared that addition produces a shift, either a horizontal or vertical shift, depending on whether the addition happens before or after the function is applied. So operations that are applied before the function are horizontal changes. We're changing the inputs, so we're going to change horizontally what happens to the graph. The operation of multiplying by b or multiplying by a, when we're multiplying, we're going to produce a stretch. So when we multiplied before the function, we had a horizontal stretch. And when we multiplied after the function, we had a vertical stretch. So those are our 4 changes that we can make to the graph with addition or multiplication, either before or after the function. So once again, let me summarize. If we write down the order of operations of what's going on, think about the order of operations of turning x into a y. The first thing that happens is we subtract c. Then the second thing that happens is we multiply the result by b. Then the third thing that happens is we apply the function. Fourth, we would multiply by a. And fifth, we would add d. That's how we turn x into y. That's just reading what the function is telling us to do. So the function is in the middle, and these are operations that take place before f of x. And a and d represent operations that take place after f of x. Operations that take place before are going to produce horizontal changes, either a shift for addition or a stretch for multiplication. Operations after the function are going to produce vertical changes. Shift for addition, stretch for multiplication. There are other operations that we could perform before or after that do different things. But we want to understand that things that happen before the function are going to produce horizontal changes. Things that happen after the function will produce vertical changes. That will always be the case. Sometimes we can phrase, depending on the function, we could phrase our horizontal changes as vertical changes. But those will be more exceptions than rules. So once again, this is one of my favorite kinds of things. We have two operations in two locations producing four things to keep track of. So if we switch over to the board to remind ourselves of what's going on, let's see, grab Desmos here, zoom in a little bit. There we go. So let me share screen. So taking a look at Desmos, I've set up in red, I've set up the function e to the minus x squared. This is our baseline function. And then I've set up in blue my function with its variations. So notice that I've got this horizontal asymptote at 0 and a local maximum or a global maximum at 1. When I do a vertical addition, if I change d to, let's say, 2, the horizontal asymptote is now at 2 and my maximum is at 3. So there's been no change vertically. There's been no vertical changes in my function. It hasn't stretched or anything like that. It just, so changing the value of the constant or the addition after the function moves the graph up and down. So if I change, let's move d up to 2. There's been no stretching, it's maintaining its shape. A shift maintains a shape and just moves the graph up and down. The other shift is the value of c. If I change values of c, if I increase c to, let's say, 1, that shifts the graph over 1 unit. Notice that the shape is maintained during a shift. The shape is maintained. We're just moving where that high point is, where that maximum is. Now, if we move our shifts back down to 0, those are the no shift, because 0 is the additive identity. Adding 0 doesn't do anything. And we start messing with the multiplication. If I change the multiplication after the fact, I should see a vertical stretch. So notice that when I multiply by 2, my horizontal asymptote stays at 0 because 0 times 2 is still 0. But the high point, which was at 0, 1, has stretched up to 0, 2. I can stretch it up further to 0, 3 if I multiply by 3. So multiplying by 3 after the function will produce a vertical stretch. I can also produce a vertical shrink if I multiply by less than 1. So notice if I multiply by 0.5, that moves the maximum down to 0.5, but it still happens at 0. Also notice that if I make my multiplication 0, everything flattens out. But if I drop my multiplication, my vertical multiplication negative, that flips the graph over vertically. So if I change the multiplication to multiplication by 2 to multiplication by -2, the negative flips the graph over. Any questions? So the other thing that we'll want to notice is what happens if we change the multiplication before. So if I change the multiplication before, let me move my vertical multiplication back to 1, the default. If I change my my horizontal multiplication If I increase the value of b, notice that that stretches or squishes the graph horizontally. The high points and the horizontal asymptote are not changing, but we're stretching or squishing the graph based on the value of b. The high point is still at 0 and 0, 1. We're just kind of pulling in those inflection points that we identified last time. So we can drop b all the way down to 0, but then our function just looks like d plus a times e to the 0, which is just 1. And that's why we look at that, see that 1. And then we can have b go negative, in which case we get a completely different shape. That's an increasing e to the x function versus this bell curve. I could put all these in motion. All right. So we want to recognize that operations that happen before the function is applied will produce horizontal changes. Operations after the function is applied will produce vertical changes. Any questions? Let's build a graph and then think about what some modifications to that graph would look like. So let's build a graph. I just want a graph with some easy to find points on it. Let's look at the graph of f of x. So I'm going to have, let's see. So I'm going to have a graph that starts, it's going to be just a bunch of line segments. I'm going to start off at 0, 2. Then this will go up to 2, 3. And then drop down to 4, 1. So I just want a couple of line segments for our graph. Here's the graph of f of x. It's line segments connecting the points 0, 2, 2, 3, and 4, 1. So I want to think about what happens to each of these points. What happens to this graph if I start changing some things? Oops, I wanted y equals f of x. So I want to draw some graphs if I start moving some things around. So for example, if I want the graph of f of x minus 1, I'm changing the function by subtraction, and it's happening after the function. F of x gets evaluated, then we just subtract 1 from the result. So here, it's addition and it's after the function. And so that means it's going to be a vertical shift. We're just taking all the values of the function and subtracting 1 from them. So So we're not going to see anything change horizontally. We're going to see a shift vertically. So I'm just subtracting 1 from all the values of f of x. Oops. Subtracting 1 from all the values of f of x. So 0, 2 will drop down to 0, 1. The point 2, 3 will drop down to the point 2, 2. And the point 4, 1 will drop down to the point 4, 0. Because I'm just taking the values of f of x and subtracting 1 from them all. So I'll have the point 0, 1, 2, 2, and 4, 0. All that's happened is that we've subtracted 1 from all the y values. Let's look at another one, another modification. Let's suppose that we have y equals f of 2x. So we're changing the graph, changing the function by multiplication, and this multiplication is happening before the function. So here we have multiplication. And it's before f of x. Before means we're going to have a horizontal change, and multiplication means we're going to have a stretch. What happens when we multiply by 2 is that we're going through our x values twice as fast. That's the read that we want to put on this multiplication before the function. When x is equal to 2, f of 2x has already got all the way to 4. So this is actually going to squish the graph horizontally. It's going to push it inwards with the f of 2x. What you want to do is think of the 2 as saying we're going through the x's twice as fast. So f of 2x means we're going through the x's twice as fast. Our original function, the 2 line segments take up from x equals 0 to x equals 4. But we're going twice as fast with 2x. That means we're going to take care of all this business from 0 to 2 instead. Because when x is equal to 2, 2x is equal to 4. Think of the x as going twice as fast. So what used to take from 0 to 4 will now be done from 0 to 2. So when I say x is going twice as fast, what used to take from 0 to 4 will now be done from 0 to 2. So rather than taking 4 units on x, it will only take 2 units on x, because when x is equal to 2, we're going to be evaluating f of 4. So what's going to happen instead of this whole graph going from what used to take this space from 0 to 4, it's now going to be done in 0 to 2. 0, 1, we don't have, the x is 0, f of 0 is 0. Oops, not 0, 1, 0, 2 is my original. But the point 2, 3 will get there twice as fast. Instead of being at 2, 3, that'll take place at 1, 3. And instead of 4, 1, we'll be at 2, 1. Because we're going through the x's twice as fast. So our original graph, we went to had that up and down. It all took all the way from 0 to 4. But now that we're going through the x values twice as fast, we've compressed that. We've got this horizontal compression. If we had both of these changes, if I want to look at the graph of y equals f of 2x minus 1, the multiplication by 2 would compress things horizontally, and the minus 1, subtracting 1, would shift the graph down vertically, down 1 unit. So now, instead of 0, 2, we'd be at 0, 1. Instead of at 1, 3, we would be at 1, 2. And then instead of 2, 1, we'd be down to 2, 0. That'd be a combination of the previous two modifications. There's our horizontal compression because it's multiplication by 2, and our vertical shift because we're subtracting 1. Any questions? All right. So I like to emphasize reading what's going on in our function to make these determinations. That's why I broke it into 4 things. That's why I looked at the previous, on the previous page. I wanted to write down the order of operations. Not order of operations as far as PEMDAS goes. PEMDAS is trash. But order of operations, learning how to read what the function is telling us. The function is just a list of instructions, a list of things to do to x. And so we should understand what order we have to do things, because we don't get to do multiple things at once. We don't get to multitask. Sometimes we can change the order, but that's only if we have if we know how the a bunch of operations will interact. Any questions? Comments?
Professor, you don't mind to explain that last 2 examples, the y equal f 2 of x.
So y equals f of 2x.
Mhm.
I've changed my original function with multiplication before the function happens. So instead of f of x, I want to look at the graph of f of 2x. So what that means is the way we can read that is that we're going through x values twice as fast. What used to take from 0 to 4, since we're multiplying all the x's by 2, now that's only going to take from 0 to 2. And that's why the graph went from going from 0 to 4, it gets compressed down because the x's are going twice as fast from 0 to 2. So this second leg got pushed in, and then this first leg, we just kind of compressed it this way.
Oh, okay. I see it now.
It's like, since multiplying 0 by 2 doesn't do anything, it's like you hold everything at 0 and just push the x values in. Cut the x values in half because we're going through them twice as fast. And then this last example, we're just subtracting 1 from all the f of 2x values. We're just taking this graph and shifting it down 1 unit.
Oh, okay. So basically we moved it down one. Okay, got it. Interesting.
And so that's how we want to read what's going on in our graphs. So if we had, for example, I don't want to make all these changes, but we want to see what's happening. This -3 means we're going to do a horizontal shift 3 units. Because it's addition and it's happening before the function. Addition means a shift. Before the function means it will be horizontal. The -1 is the vertical shift that we saw before. And we know that this is going to go down 1. The 2 is a horizontal stretch or compression. X's are going twice as fast. So that's going to compress because the X's are going twice as fast. Since it says x -3, we're doing a horizontal shift 3 units to the right. Sometimes when we look at this x -3 before the function, and we don't want to read that as a horizontal shift, and we want to read it as moving to the right 3 units. When we read the horizontal shift, the negative comes with it. It's x minus, then whatever the shift is. It's x -3. And that's why we're moving to the right 3 units. Think about it this way. In my original function, f of 0 is equal to 2. That point is going to shift to the right 3 units because when we plug in 3, we subtract 3 and then we evaluate the function. 3 minus 3 is 0. And so that's why this 0, 2 is going to be over here at 3. And it's not going to shift left. It's not shifting left just because we see negative, because the format is x minus the horizontal shift. Now, if we had a graph or an equation, a function, a modification to the function, where y is equal to f of 2 times x plus 5 minus 1, the 2 still represents horizontal compression. The -1 still represents a vertical shift down 1 unit. But since it says plus 5, we read this this part of the expression, this part of the function as x minus a -5. And then we see it's a horizontal shift to the left 5 units. Think about what gets you to 0. If it says x plus 5, it's a -5 that gets you to 0. -5 is left 5. Any questions? The inside ones seem backwards from the outside ones.
Professor, I have a question on the x plus 5, and the bottom you have x minus 5. Is that correct?
That's
Is
correct.
is this the formula?
There's no formula here. This is just reading.
Oh,
Don't think of things in terms of formula. Think in things in terms of just how they work. And when we're writing down a horizontal shift, we write x minus the horizontal shift. This is related to some things that we've seen before. So if we think about the vertex form of a parabola, we have y equals a times x minus h squared plus k. And the vertex is hk. It's the same concept. The minus h shifts the vertex from 0 to h. The plus k shifts the vertex up to k.
Thanks. I remember the vertex. Thanks, Professor.
Yeah, we're doing the same thing with the vertex because the vertex says x minus h squared, but plus k. So if we have x minus 3 squared, the vertex is at 3. But if we have x plus 5 squared, then the vertex is at -5. So that's like the most recent thing that you've done with these horizontal and vertical shifts. Sometimes what happens is we look at these horizontal and vertical horizontal shifts and we read them as being backwards. So just remember the horizontal stuff seems backwards. Eventually, you'll have thought about it enough that it won't seem backwards anymore. And you'll read the 2x's. We're going through twice as fast. You'll read the x minus 3 is like, oh, we have to start at 3 to zero out the x minus 3. So you'll read that as the start. You'll read 3 as the start. 3 is what makes this part 0, or -5 is what makes this part 0. That's why an x plus 5 is a shift left 5. If you don't see it as backwards, don't try to see it as backwards. I only say that because in math classes, we tend to be programmed with things. When you see this, do this. When you see this, do this. And we've kind of been programmed with this. Plus is to the right or up. Up is positive, right is positive. But that's just an arbitrary choice. The only reason that north is up on the map is because someone had to pick a direction. And it made sense to them to put north going up. It's probably some in an alternate universe, north is pointing down on their maps, or even to the left, or up and to the left at a 45-degree angle. Who knows? In Battlestar Galactica, they cut the corners off their paper. Why would you do that? That doesn't make any sense at all, except to make your paper look cool and futuristic. But why would you want to make all that effort to make 4 extra cuts to make your paper? It doesn't make any sense. Maybe it's built differently. Maybe they don't cut it out of large sheets. Maybe it's just extruded. I don't know. It's a cool detail to make everything look different. Why were the collars so big in Loki? That doesn't make any sense at all. That was completely excessive. But they do things like that just to make it seem different. Any questions?
I think north and south makes sense, but I'm pretty sure Earth spins around an axis, and that's why the poles are where they are.
Right, because we use the right-handed rule. And so, but what if that universe uses, what if that, because in our world, righty-tighty, lefty-loosey, but what if in that world, lefty-tighty, righty-loosey?
Ah. That's
And
weird.
it would just, and they would look at us and say, can you believe they use right-handed screws? They'll be like, oh, what? And they're like, oh, yeah. And it's like, and then they'll be like, oh, what a bunch of children. Everything has to rhyme. Lefty-tighty, righty-loosey. So there's a reason for everything. And sometimes usually what happens when we start explaining things like that is that we just kind of start going in circles. Anyway.
Professor Lich, just
Yeah.
a quick question, please. On the last example, we have the y equal f. There's a 2 right there. That is the horizontal stretch.
Yes.
Could you give me one example vertical stretch? Where is that?
Oh yeah, a vertical stretch would be multiplication after the function. So I'm going to use this one because I want to use a 3. So for example, if y is equal to -3 times f of 2 times x plus 5 minus 1, this -3 would be a vertical stretch because it's -3 times the value of the function. So this is multiplication, and it takes place after the function has done its business. So this is a vertical stretch. Also a reflection because it's negative.
I see. Verticals.
So we'll just take all the y values and multiply them by -3. Keep in mind, if we're doing two things, if we're doing multiplication and addition to our y values, we're following the order of operations. First, we'll multiply all the y values by -3, then we'll shift them down 1 unit, as the order of operations applies.
Shift 1 unit. This is in this case -1, correct?
That's the -1.
Wow, I see it now. I always get confusing with this too. Now I see it now. Sometimes the -1, it could be in front of the F2, right? Correct?
Yes.
Hmm.
So I could if this function could also be rewritten in the style that I used on the first page as -1 minus 3 times f of 2 times x plus 5. And it still reads the same way. It's -3 being multiplied by the function, and then we're subtracting 1.
Wow, this is very clear. Thank you, Professor Rich. I always get confused, but now I can see it now. Thank you.
Any questions? How's everybody okay? There are some bolts that have to be left-handed. I think if you have a bolt on something that's going to be spinning a lot, you don't want it to be right-handed because the direction of the spin will cause it to loosen. But I can't remember because, you know, when you're a mechanical engineer, when you're a mechanical engineering student, you realize, wow, I'm actually going to have to build things at work. I'd rather be a mathematician. So things only have to work in theory. And then the lab just takes place in your head. So you're always in lab when you're a math major. You don't have to like go to physics lab or chemistry lab and actually make something work. It only ever has to work in theory. I think that's why I got out of engineering, because engineering, you know, you build something and it'd have to work. And if it didn't work, you'd have to know why. And I found out usually when I build something and it doesn't work, it's because I'm not very good at building that thing. So my instructor would be like, well, why didn't your engineering project work? I'm like, well, because I'm not a very good engineer. You know what I mean? I was also applied math for a little bit, but then there was too much computer programming, and I do not like talking to computers. Any questions? Comments? Snide remarks? All right, that was a little bit of a detour into graphs of functions, not so much a calculus thing, but more of a what happens with graphs thing. And it is an interesting thing to play around with. Pick a function and see what happens if you do some operation. So not say, pick a function sine of x and some other operation like x squared, and look at the graph of sine of x squared, and then do sine of x squared. What happens if you square before the sine? What happens if you square after the sine? Or think about the graph of sine of 1 over x, or the graph of 1 over sine of x. What happens if your function, instead of just addition and subtraction, what happens if you put an exponent on, like x squared, or an x to the negative 1? What happens to the graph? Do we see some kind of horizontal changes? We should see some horizontal changes here and some vertical changes here. What are they? With this 1 over x business, horizontal changes, vertical changes, what happens? Good thing to experiment on. All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.